commence. Okay. So it's a big pleasure, a great honor for me to introduce Jérôme Lang. So, and Jérôme Lang is my colleague at l'AMSAD Dauphine. He's now the director of l'AMSAD Dauphine. We were colleagues for many years before I joined the UM6P. And Jérôme has many careers. So he did many. So he's computer scientist, and since the last 15 years, he started working very actively on computation, on social choice, and he is one of the world leader in computational social choice. They edited with many other colleagues a book, handbook of computational social choice, which became the reference in this topic. And this week he is teaching at the PhD program of the Moroccan Center of Game Theory and visiting the center. And today he is giving a seminar. So in this our series of game theory seminars, and we are very happy to have him. And, and I give him the floor.
Thanks a lot, Rida. Shukran. I'm very happy to be here and to see all of you. So you please, I mean, I want this to be an interactive talk. So if you have any questions, please don't hesitate to interrupt. Okay? So this is a joint talk with my PhD student Théo Delmazur and a PhD, a postdoc in Warsaw University, Grzegorz Pierściński, postdoc. I think he is a postdoc now. So I'm not sure how many of you know about voting. Who knows about voting, about the basics of voting? Yeah. So not all of you, but most of you. So there are different kinds of format in voting, of input formats. And one of the common formats, not the only one, but one of the common ways of expressing votes is to use rankings. Yeah. So in that case, we have a group of voters, n voters, and each of the voters has expresses a preference over the candidates, and this preference is a ranking of candidates. Yeah. And the output may be a winning candidate or maybe also a ranking of the n candidates. In that case, we speak of an aggregation function. One of the founding results of modern social choice is Arrow's impossibility theorem, which had a lot of negative implications. And so the theorem says that if there are at least 3 candidates, and if an aggregation rule satisfies unrestricted domain, Pareto efficiency, and independence of irrelevant alternatives, then it is a dictatorship. Okay, so on the next slide I will talk about independence of irrelevant alternatives, but so far I just want you to see that this kind of impossibility theorem, it's not the only one, but it's the most famous one, implies that since there is a small set of properties that are together incompatible, there are either 2 interpretations, one negative interpretation, which is that there is no aggregation rule, I mean no good voting rule, or a more positive interpretation, which means that one of these axioms, one of these properties has to be relaxed. And so in that case, chances are that it should be the IIA axiom and not the other ones. Okay, so what we want to, the message we want to deliver is that it's even more than that. Not only IIA has to be relaxed, I mean, not only it is too strong, but more than that, it may actually be a good thing to fail IIA. So what's the IIA property? The IIA property, so recall that the input consists of rankings, and one for each voter, and the output is a ranking 2, okay? Collective ranking. So IIA means that the collective choice between two candidates is independent of the positions of all other candidates. So if we focus on these two candidates here, A and B, marked in green and red, then the way the group should rank A and B depends only on the relative positions of A and B in each ranking. Does not depend on how we rank C, D, E, F, both between themselves and with respect to A and B. Yeah, so that's it. There are of course good things with IIA. One good thing is that it, to some extent, it prevents the spoiler effect. So the spoiler effect means that if there is a candidate, suppose for instance that we have a rule such as the rule that would elect the candidate that is ranked the highest number of times in first position. If you have two close competitors, okay, two candidates that have closely related programs, they would harm each other, and this is of course related to the failure of IIA. Another good thing with IIA is that it prevents the implicit use of interpersonal comparisons. Okay? We know that it is difficult for, when you want to implement a collective choice, it is difficult to compare the way to compare the way an agent evaluates a candidate to the way another agent evaluates a candidate. I mean, it's difficult to compare them quantitatively, and IIA to some extent prevents the implicit use of interpersonal comparisons. Okay, so let me give an example. Okay, so we have 55% of the voters who have this ranking A, B, C, D, E, F, and 45% who have B, E, F, C, D, A. Yeah. So because because IIA does not take into account C, D, E, F when comparing A and B, it looks obvious here. I mean, if there is no reason to a priori favor A against B or the opposite, okay, if the two candidates are equal, then there is no reason not to prefer A. Okay, so we should prefer A in that case. Is it? Do you think it's desirable here to choose A against B? No. Why? Because? Yeah, because you see that even if it's not explicit, in some sense, the preferences suggest that the first group of voters slightly prefer A and B. It's a suggestion. It's not for sure. Okay, but it looks like they slightly prefer A over B, while the other 45% strongly prefer B over A. So even if rankings do not convey explicit information about intensity of preferences, in some sense they do. In an implicit way they do. And studying this implicit way is the goal of the talk and the paper. Here's an example. I mean, the slides are not mine. I mean, these are by my student Theo. So you see, I mean, I'm a vegetarian, so I would belong to the second half here, and I mean, this piece of meat, I would rank it really last, and I would be very angry if the collective decision was to choose meat with such a profile, because I mean, I think it's important to take, I mean, in that case, to take intensity of preferences into account. Okay, so our goal is to measure the negative impact of IIA on social welfare, and the first question is, how can we do that? And so we'll see that the question is not that trivial, and you'll see how we do. So a reformulation of the goal is, so you see, I mean, this is the word, there is the adjective negative here. So the positive way is that we want to measure the positive impact of irrelevant or additional candidates on social welfare. So we want to actually send the information that the failure of IIA is a good thing. We're not the first ones to notice that, but what we do is that we are using some techniques that are used for that problem for the first time. So, the thing is that we're going to compare IIA to you know, when we want to compare two candidates, A and B, okay, IIA defines implicitly a rule which most of the time is the majority rule. I mean, if candidates are equal, it has to be the majority rule. Okay? So when we say IIA, we often mean majority, and we want to compare what majority says about A and B to what other voting rules that take other alternatives into account, other candidates into account, would say about A and B. And so we need to define rules that only choose between A and B, between two candidates A and B, but that take other candidates into account. Okay, so the input consists of rankings over many candidates, more than two, but the output is just a ranking of two candidates. Okay, so we call that pairwise voting rules. Okay? Majority is, of course, a pairwise voting rule, but there are plenty of other pairwise voting rules that, I mean, most common voting rules can be turned into pairwise voting rules. Okay? No, that's, yeah. And the techniques that we use to measure the positive impact of the failure of IIA is distortion, is voting distortion. So this is a very important topic right now in the social choice community. Who has heard about voting distortion? Okay, very good. Okay, just only read that. So the implicit assumption in voting distortion is that even if they don't express them, voters have numerical utility, quantitative utilities over candidates. Yeah. But we don't ask them to specify these utilities, but we know they have utilities. Yeah. Or sometimes they have costs, okay? So yeah. If they have utilities, then of course they should be consistent with their preferences. Okay, so if a voter says I prefer B to C to D to A, of course, I mean her utility for B should be higher than her utility for C, and so on. Okay? So you see, in a sense, of course, I mean there is an implication from expressing quantitative preferences to expressing rankings. I mean, if you know the utilities, then you know the rankings. Yeah? the other direction, in principle, you cannot infer more from the rankings than just the ordinal comparison of the utilities, but in practice, you know a little bit more than that. Yeah. So the distortion of a voting rule is defined as the ratio between the total utility of the optimal candidate, which we often call also the social welfare of the optimal candidate. I'm going to explain what we mean by optimal candidate, divided by the total utility of the candidate selected by the rule. Okay, so this is something which is always which is at least one, of course, because the optimal candidate has always a higher utility, at least as high utility as the candidate selected by the rule. Another way of casting the distortion problem is to use a metric space and to have both voters and candidate located in this metric space. So you see here candidates are depicted by letters and voters by human symbols. Yeah. And so if you pick a voter, then the voter generally prefers candidates that are closer to them to candidates that are farther. Okay? So here, I mean the preference follows the distance. I mean the farther, the less preferred. Okay, and we do that for, of course, every voter. Okay, and of course, I mean for each candidate, so you can aggregate you can take the sum of the distances of the different voters. Okay, and the distance can be seen as a cost. Suppose that you want, the candidates are positions where you should build a new university. So, for instance, when Morocco decided to build the University Mohammed VI, maybe there were a few different alternatives. I don't know, but everybody wants maybe the university to be close to where they live. Okay, so this is an example. This is called facility location. Yeah. And of course, we want to minimize the social cost of the candidate. This is minimizing social cost, but with a non-anonymous aggregation function, where some voters count more than others. Yeah. Okay. So you remember that with utilities, the distortion was the utility of the best candidate divided by the utility of the outcome of the rule. And for metric distortion, this is the opposite because we want to minimize cost. So that would be the distortion here is the cost of the candidate selected by the rule divided by the cost of the optimal candidate. Okay, so that was worst case voting distortion. We can also study average case distortion. So here we need to start with some distribution, some priority distribution over the positions. I'm talking about metric spaces here. The average case makes more sense here in the metric case because it's more constrained. I mean, I can say more about that. Yeah. So there is a distribution about the positions, but the locations of voters and candidates in the metric space. Okay, and for each pair of candidates, we can compute the pairwise distortion of the rule. So yeah, first we sample a profile. So we sample profiles for each profile. Okay, for each profile and each pair of candidates. Okay. We compute the pairwise distortion of the rule, okay? And this actually I think I forgot to say something. I forgot to say this. When I have to come back to here. Let me come back to here. So, in classical distortion, in the classical literature on distortion, the winner can be any of the candidates, okay? So both the optimal winner and the winner are selected by the rule, but here we focus on pairwise voting rules. So the distortion, the pairwise distortion, is the cost of the candidate among A and B, okay, selected by the pairwise rule, divided by the cost of the optimal candidate among A and B. Okay, so this is exactly like classical voting distortion, except that in both cases the candidate we choose has to be A or B. Okay, so again, so average pairwise distortion. So we sample a profile using some distribution. For each pair of candidates, we compute the pairwise distortion of the rule, and then we compute the average of all pairwise distortion. Okay, so here, I mean, so we have an example where in many cases you see all cases in green, the optimal candidate. I mean the optimal between A and B coincides with the candidate that the rule outputs. Okay, and in the red cases it's not the case, and in that case in those cases we compute the ratio and we get yes.
About the results. So will the result depend on the dimension you are going to suppose for the space and the distribution you are going to?
You'll see that later. Okay, so here when we compute the average, so the average of all pairwise distortions, and then we have to average over all profiles that we can sample. Okay, so what my student Theo did is that he studied average distortion both using distributions and also using real data sets. Okay? So instead of sampling, you just takes real data sets. Yeah? And he considered, for sampling, I mean, he considered a few classical distributions. Yeah? Okay, and what we find is that, okay, so on the left we have the uniform distribution over profiles, okay, which is not the most realistic way of sampling profiles, but the most obvious way, and it's still a classical way. Yeah. I'm not showing the results for other distributions, but I mean, in that case, I mean, the results would be similar. So we found, we find something which is absolutely not surprising, is that, so first, I mean, I have to explain what we have in the X and Y axis. In the X axis, I have the number of candidates, okay? So recall that I have an arbitrary number of candidates, okay, here up to 15, but I use pairwise rules, which means that I always select between the two candidates I start with, between A and B. And voters, they don't vary here, so I don't remember how many voters, but I mean, how much it varies with the number of voters is not the most interesting thing. Okay? It's more interesting to see how it's, I mean, I have to find that in the paper, how many voters. It's more interesting to see the variation with the number of candidates, because the idea is that if you add more candidates, then you get more information to choose between A and B. Of course, if we use majority, if we use the rule that satisfies IA, then other candidates, we don't use the information about them. So whatever the number of candidates, the the distortion should be the same. Right? Yeah. And the average distortion, you see, it's something, well, it's not very far from 1. It's something like 1.01, a bit more. You know? Also because in many cases, I mean, we get something satisfactory. You know? But still, it's more than 1. And of course, it remains constant because we don't take other candidates into account. Okay? But so if we compare other pairwise voting rules with majority, then we get one which is much worse, especially when M increases, when the number of candidates increases, which is plurality. So why is it the case? Is that, well, plurality, so recall that, I mean, plurality, we count the number of positions that the number of first positions, of top positions that each candidate has. And we rank the candidates according to that. So for instance, suppose that we have 15 candidates, okay, and 100 voters. Okay? If we use majority, maybe we would have that, we get that 55 voters prefer A to B and 45 prefer B to A, so we choose A. Okay? Now, if we use plurality, then we lose a lot of information about A and B because there will be only a few, maybe 7 or 8 voters who prefer A over all candidates, and also maybe 7 or 8 who prefer B against all the other candidates. And then other voters, they would prefer other candidates. So this doesn't send any information about A and B. And when the number of candidates increases, we lose all the information about A and B. So this is why plurality is so bad. All the other rules are better than majority, and which was expected. Two that are, so I'm showing here only 5 rules in total. Theo has many other rules in his experiments, but the one that does really well is the border rule. Who knows about the border rule? So I need to explain. The border rule is a rule that is such that when a voter ranks, say, A, then B, then C, then D, then E, okay, then you would give a number of points to each candidate, and these points decrease by 1 unit for each rank. So if you have A, B, C, D, A, then A would get 4 points, B 3 points, then 2, then 1, 0. And then you sum the number of points that a candidate receives from each voter, and of course, I mean, the winner is the candidate that receives the largest total number of points. So the border rule fares particularly good here. With the Copeland rule, I'm not going to explain, that also fares quite good. Yeah. On the other hand, for real data sets, so Theo used restaurant ratings where people evaluate restaurants with numeric mentions, evaluation, qualitative evaluations. Yeah, it's étoile, yes, yeah, with the number of stars that are between 0 and 5. Okay. And so he converted that into rankings, breaking ties somehow. And we find something similar, that plurality is really bad, and the other rules are ranked the same way as for impartial culture, the uniform distribution. And we get, I mean, this kind of the relative positions of the different curves for different rules is always the same. Yeah.
For the other distribution, other than the uniform, you find something
similar. Yeah. No. Well. Yeah. I must confess, I don't remember. I mean, I believe so.
Yeah. It's not surprising for both. Because you can justify both that by some uniform distribution. So this is, in fact, the Laplace.
Mm-hmm.
You know this paper of Laplace?
No.
The book of Laplace?
No.
So So Laplace computed. Imagine the model in which voters have the utilities numerical drawn from some uniform distribution, but you observe only the ranking. I'm speaking about Laplace, del Laplace. And then what should be from the preferences? What should you give as numerical values? Then they should be spaced in, like you decrease by one.
So he invented the border rule.
He justified border.
He justified the border rule. But was Laplace after border or before? After border. Yeah.
It was calculation justified border. Then you give another method, which is imagine I want to discover the probabilities of events. Now, if you give a ranking, it's the more likely event, second more likely event, third more likely event. So you should have some distribution over the ranks, such that the sum should be equal to 1. So now the number should be equal to 1. What should be these numbers? And there is a formula with some numbers computed using probability.
Yes.
By Laplace. So it's very, very fascinating.
Okay. You need to give me the reference because it looks like. So what we did is maybe totally subsumed by what Laplace did, maybe.
Laplace didn't do median; he did the sum of the.
But we did do the sum as well.
Yeah. So Laplace was really.
So
that Laplace was interested by voting.
Yeah.
Because we don't know him for voting.
But maybe we're doing the same thing as Laplace.
So it's related what you do somehow.
Yeah.
Distortion, what you said, is somehow related to Laplace spirit.
Okay. I'm not even sure that people who work on distortion know that.
I don't know.
Yeah. Okay. So now let's talk about worst case pairwise distortion. So let's focus on the metric distortion because it gives neater results. Worst case distortion is often more interesting in the metric case than in the non-metric case, than in the general case. I mean, first question is what is the worst case pairwise distortion of the majority vote? Then actually this result is a reformulation of something that is already known, by the people who worked on distortion. This is one of the first results in the papers on distortion. It's that when so if you have two candidates, A and B, that I depict them on a two-dimensional space, but you can see them on a line. They are on a line. And you see that you have A and B at the two extremities of the line, and there is a little bit more than half of the voters at the middle of the line, but a little bit closer to B, and the rest of the voters are located at the same place as A. So you see that if you apply majority, you would select B because of this 50 plus epsilon %. And what's the ratio of the cost? Well, for the blue candidate, for the green candidate B, so there would be suppose that the distance between B and these voters is 2, and you have around half of the voters, so that would be 2 times 0.5 plus 1, which is the distance here, times 0.5 as well, so that would be 3, And the cost of the optimal candidate, well, the optimal candidate is A, because half of the candidates here, the distance is 0, and for the other half, it's 1, So if you take the ratio, that's 3, So that's a result that is well known, and that's, of course, I mean, this 3 is a lower bound. I mean, it means that for any voting rule on a metric space, you can't do better than 3. So now focusing on pairwise distortion, the question is how can we yeah, so we want to compute the pairwise distortion relative to A and B. And now we have some information, some more information about A and B by having the rankings of other candidates. And we ask the question, can we decrease this bound 3 by choosing the position of the other candidates? Okay, it's like, I mean, you can choose the positions of the other candidates on the map so as to maximize the information you get about A and B. So that's the cooperative version of worst case pairwise distortion. And there would be now an adversarial notion, okay, where in that case we take the opposite point of view, where we try to choose the position of the candidates to make the bound worse, okay, to make the. So depending on whether the additional candidates are located to help you or to harm you, you get, of course, very different results. Okay. So you can see these cooperative and adversarial versions as in a using some interpretation of whether the agent who, yeah, if the agent who chooses the positions of candidates is cooperative, then you can call that an optimistic case, and otherwise it's a pessimistic case. Yeah. Okay, so we know that the majority pairwise rule as a worst case distortion of 3. We saw that before because other candidates don't count. Okay, and then we want to see how other rules are located. Plurality veto. So I will not explain other rules. I mean, if you're interested in knowing what these rules mean, I mean, just come to talk to me and after the talk. So plurality, veto, and instant runoff voting have the same distortion 3, okay, even when you add candidates. So talking about worst case, those rules don't perform better than majority. K approval. So K approval is the rule where each K is fixed, is a fixed integer between 1 and the number of candidates, and each voter gives 1 point to each candidate ranked in the first K positions. That's K approval. And so we get that K approval has worst case distortion 2 when the number of candidates is at least 3. So 2 is better than, of course, is better than 3. Then we can do better, and that's Borda. The Borda rule has worst case distortion m plus 1 over m minus 1, which tends to 1. So that's a very positive result about Borda. Of course, I mean, we could ask the question, is Borda the best positional scoring rule? So a positional scoring rule is a rule that generalizes Borda and plurality, those two rules I talked about, where there is a vector of scores, S1, S2, and so on, so that when a voter ranks a candidate in position 1, the candidate gets S1 points, and when it's in position 2, that's S2 points, and so on, and you sum the points and you maximize. Okay? So we could wonder whether Borda is optimal among all scoring rules, considering worst case distortion, and it's actually not. Okay? There is a variant of Borda that Theo called odd Borda, actually for 2 reasons, because odd, you know, in English it means not even, but it also means weird, okay? And so and you see these are odd, the scores are here are odd numbers except the last one, okay, 7, 5, 3, 1, 0, but it's also weird, okay? So the result is weird, actually. Yeah. So there is an explanation which I forgot a little bit, but if you give me time to find it. Anyway, the difference is not that huge, but still it's a little bit different. Okay, so we know that odd Borda is optimal. Yeah, and by the way, the ratio is that 2m minus 1 over 2m minus 3. Right? So it's almost the same as Borda. You can see that on the figure, but it's a little bit below. So what we don't know is that if we can do better, not only among all positional scoring rules, but over all pairwise rules, and this we don't know, but we know it's true for at most 5 candidates. Yeah. That was for optimistic positions of candidates. That was for the cooperative case, yeah, where you can choose the positions of the candidates. For the pessimistic positions of candidates, or adversarial, then things are, of course, less positive. So we see that we know, of course, that majority still has distortion 3. And plurality, veto, IRV, and K approval have infinite distortion. So we can find counter examples where the positions of the candidates are located such that, we lose all information about A and B, and we can get actually, this is the case for all rules that pay a lot of attention to the candidates that are ranked on the top. Yes?
Can we interpret these two results as, let's look at the best distribution somehow, from which we are going to generate our data, and the other one is the worst distribution?
Yeah, but here it's worst case.
The candidate is somehow choosing the distribution.
Ah, yes, I see. But we are going to add candidates. Yeah. But here, actually, the choice of the nasty choice of locations depends on the profile. Yeah. It's an adversary, so you see that it's the devil. You see, so they see the profile and then they
the profile.
So that's very bad for those rules that give a lot of importance to the tops of the votes. Yeah. And for Borda and odd Borda, which gives equal importance to all positions, then we get much more positive results. Still the distortion tends to infinity when the number of candidates grows. We see that actually the distortion grows linearly with the set of candidates. So that's not that positive, which means that actually the worst case distortion is actually worse than majority. But this is less severe than with plurality or IRV. Okay. I don't remember where. So I'm going now to the conclusion. So the conclusion are, there is no uniform conclusion. Conclusion depends on what we are doing. Right? So the impact of satisfying the IIA property on social welfare can be mild to very bad depending on the context. Okay. And even in some contexts, it's good. You see, with adversarial candidates, with adversarial positions of candidates, of additional candidates, it's even good. It's even better than other rules. But for worst case distortion and cooperative positions of candidates, it's good. It's good to violate IIA, and also in the average case and in the real dataset case. Yeah. So the lesson is that except for worst case distortion with adversarial positions of candidates, additional irrelevant candidates do provide useful information. Yeah? And this information is better used by some voting rules than some others. And with the Borda rule being the prominent rule, and also its odd variant. And this raises the question that has been, of course, asked many times in the social choice community: is the IIA property only bad because it implies dictatorship, or is it bad intrinsically, independently of this property? To reformulate that, if Arrow's theorem was not true, still, would we want to satisfy IIA or not? I have the feeling that IIA is intrinsically bad. That I'm done. Well, no, I'm not totally done. So this is a QR code to the paper. And in the paper you'll see that there are many other figures where you see that Borda is always the best here, and Copeland just above, and plurality is always the worst. I'm done. Questions? Yes.
Jérôme.
Yeah, Rémi?
Thank you for the presentation. My question is, I feel like because in everything you presented, you assume that candidates exist, like the number of candidates and their positioning in the metric space, when there is a metric space, is exogenous and something that is fixed. But I feel like IIA is something that is done to prevent candidates from strategizing whether they run or not, and whether they would try to modify the positioning in the space. And so, what do you think about that? Do you think that maybe IIA is desirable in this regard? I can elaborate a bit more if my question is not clear.
Yeah, I see what you mean. You see, in the interpretations that there are many interpretations in which it is a little bit difficult for candidates to cheat, to report in the metric space. If these are locations of facilities, it's a little bit hard for candidates to cheat about their positions. It is true for political elections and political programs. That's very true, and we see that every day in many countries. But for facility location problems, that would be hard, and also for data sets about restaurants, and then it's a little bit difficult for candidates to cheat. They have no power, and well, they can do better food maybe, but they can't really cheat So your question is indeed tell something about political elections. Yeah. So but I have no answer. I
understand your conclusion that IIA is not a very good property, but so would you say that it's not so bad when it's used for political elections, or?
No, I would continue I would continue saying that it's bad. Of course, there would be the need to do a study where candidates are allowed to change their positions. I believe IIA is still bad. My own feeling is that it is still bad. Yeah.
Do we have questions from the audience, from Teams? Edith or... Okay. So, small question. Since I worked on voting systems in which you asked the intensity of preferences, and this is what we see here, the problem comes from the fact that we don't have this expression. When you say, in your first example, we feel that here probably A is a little bit more preferred to B, and in the second case, stronger. So adding more candidates, if there is some underlying metric space or distribution, will help, because it helps us to say, okay, if I add candidates, there is no, it should give me some information about this feeling, okay? And but now, if you can have scale or some intercomparison, then this problem is solved somehow.
Yes. I totally agree. Yeah.
So my question now is, what are, in your opinion, the instances in which there is possibility to have this intercomparison and where it is more difficult to have it? And I will emphasize that even in intercomparison, you have two possibilities. You can have numerical values, or you can have values that are ordinal, but still with intercomparison. But not necessarily if you say good, bad, or excellent, blah, blah, blah.
Yeah, there is even something intermediate where you can, there is an ordinal notion of intensity of preferences where you would say, I prefer, I mean, the difference between A and B is larger than the difference between C and D. You can, I mean, using this, you can already do things.
Yes. Sure.
So you are asking me in which practical context it would. For
example, rate in a restaurant was an example. For example,
sure.
What they use, they use this not numerical because it's 0, 1, 2, 3, 4, 5, but they aggregate by using the mean. So they aggregate like numerical values, but they don't give intensities to start with. But at the end, they give. But for people, when they give 5-star and 4-star, do they use them in, you know?
Yeah, if I understand your question, so you're saying there are two ways of, at least two ways of getting people express intensity of preferences. Either they do it explicitly by reporting values, whether numerical or non-numerical, they report values, or they do it implicitly by giving rankings using these using assumptions that come from distributions. Okay? And is this your question? And is the question is when is it good to do one or the other? If people are really capable of giving evaluations, like typically in rating restaurants, for sure they are capable, then why not do that, indeed? When ranking candidates running for an election, I'm less sure it. I would say,
it's just personal.
Yeah, I know.
There's no theorem. You can.
But I know you.
From your experience.
I really maybe they're more asking them to report ordinal information. Sometimes looks more homogeneous to me, but this is really a personal taste.
So let's thank Jérôme Lang a lot, and it's the first talk I think we have on voting since the beginning. Probably, perhaps Edith. It was a little bit also multi-winner elections. So
was it on participatory budgeting? Participatory budgeting is very much related to voting.
So just to say that game theory is not only strategic game theory; it's also cooperative games. And if you look at the book by Fundamental and Morgenstern, that was the founding book of game theory. I think in this book, except zero-sum game. All the rest was cooperative games. So the cooperative game is also game theory. So thank you for everybody, and see you for next talk.